We have had a set of very interesting talks over the last 2 days, and we again have 4 talks lined today. And in the spirit of how we have been doing things, we again begin with a tutorial talk today. The speaker for today's talk is Professor Mahesh Panchagnula. He's from the Department of Applied Mechanics. Professor Panchagnula has obtained his BTech from IIT Madras and then subsequently did his MS and PhD from Purdue University in mechanical engineering. After a stint in Lehigh University, he was a faculty in Tennessee Technological University. Since 2010, he has been with us here at the Department of Applied Mechanics. And besides being a professor here, he also shoulders the responsibility as the Dean of Alumni and Corporate Relations. Today, he's going to give us an introduction to chaos. His research interest is in fluid mechanics, atomization, and experimental fluid dynamics. So eagerly looking forward to this introduction to the world of chaos. Please go ahead.
Thank you, Anubhav. I hope you can all hear me. Thank you and welcome to this afternoon's kind of a tutorial session on chaos. I'm sure all of us learned this word chaos very early on in our, when we were learning English. But in this world, it has a very formal definition. So at the end of this talk, I would like you to go back with at least 2 takeaways. One is the formal definition of the word chaos. It is not the same as the English definition of the word chaos, of English meaning of the word chaos. And the second aspect is kind of a physical feel for what this world of chaos looks like. So I hope to have those 2 ends accomplished in about an hour. We'll leave about 20 minutes or so for any questions from the audience, students, and anyone else that is on this talk. Okay, so I will, for those of you that would like to write to me for any purpose of, either related to this talk or not, I will indicate my email address here. You're welcome to drop me a note if you have any questions later on as well. Okay, so let's go in. I mean, like I promised, we learned this word as an English word long time ago. If you notice, the word chaos on this slide is with a lowercase c, whereas when I use the word chaos with the uppercase c, it is the real physics term chaos. So the Merriam-Webster dictionary meaning of chaos is that there is an inherent unpredictability in the behavior of a complex natural system. Apparently, the meaning of the word chaos as defined by Merriam-Webster has borrowed from the world of physics. This is not what we learn as the English connotation, but it's pretty close to the physics meaning of the word chaos. This actually came to me as a bit of a surprise that Merriam-Webster has adapted the meaning from the world of physics. Now, dynamical systems whose states are apparently random. So the key word here is this apparently. Okay, we'll come back to see this in a few different examples. Whose apparently random states of disorder and irregularities are actually governed by underlying patterns and deterministic laws, just that they are highly sensitive to initial conditions. Okay, so one of my favorite examples at this point is a coin toss. Okay, now I'm presuming all of the audience members have some grounding in mechanics. We all learned the Newton's laws. So if I take a coin toss, just a coin and I toss it up, there's a certain impulse I've imparted to the coin. As a result of that impulse, there's both an upward momentum and a torque impulse that gets imparted to the coin. And assume for a moment the coin is being tossed in perfect vacuum, so no drag from any kind of an air from the surrounding fluid. This rotation reaches a crescendo at some height, it falls down, it hits the ground, bounces a few times and falls. Right now, every act in this whole process is purely governed by Newton's laws. There is nothing in here that is not governed by Newton's laws. So in principle, one would like to believe that if I exactly knew the impulse I imparted to the coin, I have a mathematical framework in which I can predict the outcome with 100% certainty. Because every little rotation of the coin, what the coin does when it hits the ground, let's say if I knew the coefficient of restitution of between the coin material and the ground, and the final outcome of, I know the initial velocity and angular velocity prior to impact, and from the coefficient of restitution I know the conditions after impact. So from all of these calculations, presumably it is possible to calculate what the final outcome would be for a given set of initial conditions. The only problem is that the reason we treat coin toss as a quote unquote associated with some randomness, meaning with some probability, is because it is highly sensitive to initial conditions. So in other words, if I knew the initial condition to arbitrary certainty, then I could predict the outcome exactly. But any less certainty than arbitrary precision would leave me stranded in a world of probability. We will see examples of this moving forward. So the whole underlying framework of chaos is a system which is governed by the laws of dynamics, but just that this sensitivity to initial conditions causes a certain randomness to apparently be manifest. So chaos theory is the mathematical approach to modeling patterns in such dynamical systems. And, without much ado, I'm going to tell you that you need to have a system to be nonlinear for chaos to be manifest. We'll see examples later on. And so any form of nonlinearity, and you will see some systems with the simplest of nonlinearity give rise to some very complicated chaotic patterns and attractors. Okay, so now let's deep dive into a very simple system. What I have here is a double pendulum. So I'm going to start this video. So there is a theta 1. So I'm going to draw a sketch here. So imagine this is the double pendulum. There is a theta 1 and a theta 2. Okay, these are the 2 degrees of freedom of the system. So we start with a certain initial condition, and you'll see the behavior of that double pendulum. On the left hand pane, you're seeing the actual mechanics of the double pendulum, the motion of the double pendulum, so to say. And on the right hand side, on the right hand side, you see the same motion represented in the form of what is called a phase portrait. We'll see a phase portrait description very often here. So in this particular case, we started with that initial condition, and the trajectory progressed kind of like that. And I don't want to follow these arrows all the way through. It's going to become quite messy. And it ended in that state finally that you see here. So I'll play this video one more time. Okay, now you see this kind of bobbing around. It's a fully conservative system. There is no dissipation in this system. So whatever is the initial energy is conserved through and through. As time progresses, you see that the motion is pretty complicated, but every bit of this motion is governed by the simplest of the laws of mechanics. Okay. Now, in the phase portrait, you can see that there is no real predictable behavior. There is no like a time periodic motion, like a simple pendulum of small amplitudes would execute what we all know as simple harmonic motion. Right now, a nonlinear pendulum of finite amplitude also executes a limit cycle, which is a cyclical motion. We'll see examples of that later on. This doesn't seem to show any of those, and neither is it promising to come to rest because it's a conservative system. It doesn't dissipate energy away. It's going to continuously move ad infinitum forever and ever and ever. So what is this system going to do? This system is basically it's got 2 degrees of freedom in theta 1 and theta 2, but really it is a 4 degree of freedom system because you have theta 1 dot, theta 2 and theta 2 dot. So when you look at a reduced order phase portrait in the theta 1, theta 2 plane, or theta 2 versus theta 1 plane. You see, it looks like these trajectories are apparently crossing, but remember, trajectories on a phase portrait never cross, because the moment two trajectories cross, at that point you have a non-uniqueness in terms of the direction in which the phase portrait can evolve. So in the four-dimensional theta 1, theta 2, theta 1 dot, theta 2 dot phase portrait, in that four-dimensional uh, space, the trajectories never cross. And so in that four-dimensional space, this system is going to continuously meander within the frame, within the limits of minus 2 pi to 2 pi being, or theta being minus 2 pi to 2 pi, and theta 1 being like, minus 180 to plus 180. So in that space, it is going to continuously evolve. And the reason this system is chaotic is what you will see in the next slide. What I'm showing here is the exact same double pendulum, except there are four panels here. They are all starting with, can you see my mouse? You'll see this. You see this. The initial condition here is 120 comma minus 10. The initial condition in the other one is slightly off. You see only in the second decimal place in each of these cases. Okay. So I'm going to play this video. It's going to last about 20 seconds, and we're going to pause in the middle. Okay, let me pause there. It's about 2.5 seconds into the video. You see that even this small sensitivity in the initial condition has not really impacted the dynamics in any big way. Okay, they're all still in a very similar, visibly similar state. Okay, so now let's evolve further. You see again, not much of a change. There you start to see some differences. Those of you that have a keen eye would have picked up why these differences come. Now I'm going to rewind. Now remember, at time 6.7 seconds, there was a difference. So I want you to pick out physically in your minds, what is it that made this difference? Okay, I'm going to rewind and start playing again. Okay, that's at 3 seconds. By this time, there's been already a big difference. Okay, now some of you who paid careful attention would have picked out a particular reason why the one in the left bottom panel is very different from the others. Okay, now I'm going to continue playing this just so you can appreciate this core idea. Okay, now this is the end of about 20 seconds. You can see that none of them look alike. So these the trajectories associated with these four double pendula started in a very small space of initial conditions in the theta 1, theta 2, theta 1 dot, theta 2 dot space. But as they evolved, the trajectories associated with these four systems have diverged quite a bit away from each other. Okay. Now, the answer to why this sensitivity arises is a question I think we need to all understand at this point. Okay, now I'm going to talk about a very simple model to understand why this sensitivity arises, and then we will go into a deeper discussion of chaos itself. So I'll start with a very simple physics problem, which I'm sure all of us are very familiar with. So let's say I have a ground, and I'm injecting a ball at this ground at some velocity vector v1 for completeness. We know theta incidence. Now, Imagine a pure specular reflection problem. So if I know the initial condition, I know the final outcome such that theta r equal to theta I. There's nothing uncertain about this. It's a simple conservation of energy and a coefficient of restitution, conservation of momentum in the horizontal direction, and coefficient of restitution being 1 is sufficient for us to arrive at this conclusion that for a given V1, I can fully determine V2 with 100% certainty. Now, if V1 were to change slightly, let's imagine I add a small delta theta I. I know what V2 would be. There would be a delta theta R that would be equal to delta theta I. No problem here, right? So as far as this problem is concerned from a perspective of mechanics, there's nothing indeterminate or nothing undeterminable about this problem. Now I'm going to take with the same physics except in a slightly more complicated geometry. Okay, I'm now going to inject a ball to come in at a velocity vector v1 here at this wall. Okay, what I have here is a T. Okay, imagine a little groove. Okay, imagine a little groove in which I'm injecting this ball at some velocity vector v1. Now I want to ask the question whether it will go to the right branch or the left branch or bounce back. There are three possible outcomes. This ball would go around and end up passing out of this domain through the left branch, the right branch, or bounce right back towards where it came from. Okay, now each little reflection from this wall is a specular reflection problem, just like the previous one. So let's see if I can draw this unit normal here, extend this. It's going to travel along a straight line till that point, and then it's going to travel along a straight line further down. And you can see that this is going to end up in the left branch. Now, if I make a small change here, let's say like that, okay, now I'm going to end up going into the right branch. So I'm going to mark this trajectory in red, sorry. And this trajectory in black. Okay. Now imagine I start out farther away. Now every bounce here, this is a simple problem. Now imagine I do the same thing with a much longer shoot where I have many different reflections. A small change in the initial condition. I'm going to approximate here. May end up going into the right branch. You can see where different initial conditions are leading me into different branches. Okay. Now, what is the core problem here? Now, this is also a simple model. Let's complicate this a little further. I have the same exact geometry as I showed just a minute ago, except I've now placed little spherical balls on this wall. Now, every reflection is still only kind of determined by the same laws of reflection, except now if I inject this ball, because of the nature of certain reflective conditions. So for example, a small change here coming this way versus something coming at a slightly grazing angle, you can see how the outcomes are going to be In this particular case, it may bounce right back, and in the other case, it may go forward. So these conditions where you have, these are the points that make a big difference and bring in this sensitivity to initial conditions. Okay. A very similar example of coin toss. Let's take a coin toss. I'm going to draw a coin. Let's call this heads and this tails. It's spinning in some direction, and let's assume for a moment it's just dropping down. Okay, when this coin hits the ground, okay, let's assume for a moment that it hit the ground nearly vertically, kind of like that, with heads on that side and tails on this side. There are two possibilities. When I say nearly vertically, if the inclination happens to be small, have a small tilt towards the tail side or a small tilt towards the head side, are going to result in vastly different outcomes from a bounce perspective. Okay. So a near vertical, the point is that this point here is kind of like a separatrix. So this condition where the coin is perfectly vertical is like a separatrix. On either side of the separatrix, if the coin fell little bit off to the leaning to the left or leaning to the right, would lead to a different outcome. Okay. Now imagine multiple such bounces where every time the coin hit the ground, there could be multiple cases where the coin hits the ground vertically, and that would change the outcome. So if you go back to this case here, this point where the ball went and hit this part of the sphere at normal incidence is kind of like a separatrix. To the left of that, you see it's going to bounce off towards the T. Towards the right of it, it's going to bounce back towards the stem of the T. Okay, so these separatrices are essentially, the word separatrix, as you can see, is it separates two things. What are the two things? In this particular description, it separates two outcome spaces. And the two outcome spaces are now determined by this point here, which is, as you will see later on, is a point of unstable equilibrium. So a coin standing on its side is an unstable equilibrium point. Slight tilt one way or the other is going to cause it to go one way or the other. So you see, every unstable equilibrium condition is going to cause us some separation of outcomes. Now, it is not truly a domain separator, it is a separatrix, and we will see kind of a little more mathematically what it ends up meaning in the context of a chaotic system. So let's go back to the presentation briefly. This is a good point for us to start looking at some examples of where these chaos happen. So I hope you are beginning to appreciate from a physics perspective, where does this sensitivity to initial condition arise from? Okay. So now any natural system or a physical system where you have unstable equilibrium points and potentially a large number of them is a case where you could end up seeing chaos. So let's take some examples. Now I want to make a distinction. I don't want to dwell on this point too much, but I do want to make this distinction between a stochastic random system and a chaotic system. Okay. Now, some of the terminology here is a bit, it's a bit beyond the reach of an introductory lecture, but let me just make the description anyway. If I had a system, very simply, if I write down a system like some dx vector dt equals some eta of t, okay, where eta is a vector of random variables. This will look like the system is unpredictable. The solution for a system that looks like this will look kind of unpredictable, just like the theta 1, theta 2 plot that you saw. But and you can kind of make it look smoother. Like a simple system like this would even lack smoothness, but you can define a stochastic system that shows smoothness. But the core idea here is that the space in which all of the outcomes would remain constrained would is what is called, is the dimensionality of that space is called it's called an embedding dimension. In the case of a chaotic system, the embedding dimension is essentially, the embedding dimension can be large, but the correlation dimension remains finite. In the case of a random system, the correlation dimension, meaning the dimension in which the different degrees of freedom and the state space variables in the different degrees of freedom show correlation, is unbounded. Okay. Now, more simply put, if I have a chaotic system, as you will see later on, the sensitivity to initial condition is something that will not be present in the most rigorous sense that we will define in a random system. Okay. Okay, good. I'll come back to that point in a little bit, but let's look at some examples of where chaos can be observed around us. Now, weather. All of us have our favorite weatherman on Twitter now, and none of them can go beyond 5 days, 6 days. So, in fact, I did a small study long time ago where, forget all weather modeling. If you just took yesterday's weather and predicted it today, you'd be accurate more than half the time. So you'd be doing better than a coin toss by just taking yesterday's weather today. Now, that is for short-term weather prediction. Now, if I know that this weather movement is a completely well-determined mechanics problem, meaning the motion of clouds, whatever patterns there are, and you know how systems evolve, you have a certain set of laws written down, why would you not be able to predict ad infinitum? Answer is, small changes in the weather patterns today will make a big difference 6 to 7 days later. We saw this in the case of the double pendulum. After about 6 seconds, there was predictability, even though the initial conditions were slightly off from each other. But at about 8, 9 seconds, the double pendulum became unpredictable purely from the. So if I knew the initial condition for those 4 pendula only to the first decimal, remember, the initial conditions varied in the second decimal place. So if I knew the initial condition only to the first decimal, I would not be able to distinguish, for God's sake, why are these 4 pendula that are apparently identical, quote unquote, identical in initial condition, behaving so differently, right? In fact, that is exactly where the world of chaos took birth, in a simple experiment, in a simple computation that a man named Lorenz was doing at MIT. He had this old computer in the 60s where, it was a finite precision. I don't know, I can't remember exactly what level of precision it was. But to that level of precision, he had defined the initial conditions, accurately. But when he ran the simulations for a long enough time, and it was a model of climate and weather, when he ran the simulation on multiple days, he would get multiple answer on multiple days, and he simply couldn't fathom why the answer was not the same. In the world of computing, we have a very simple adage. It says, if you always do what you've always done, you'll always get what you've always gotten. And in the world of chaos, he saw that that was not happening. So he had his grad student check all kinds of things with the computer. And then he realized that what he was seeing was not any error in the computing process, but something very, very exciting in the physics itself, this sensitivity to initial conditions. And that is basically where you start to see this predictability defying us after a finite time span of, let's say, 5 days, 6 days. Okay. Another very interesting, very simple but interesting experiment is dripping faucet. Okay. You can all, if any of you is excited about this world of chaos, by the end of the day, you should be finding a faucet close to you, like I did many, many years ago. The experiment is very simple. Okay. Imagine you had a faucet with a leaky washer. If you tighten that leaky washer as tightly as possible so it's dripping very gently, let's assume I can make it drip 1 drop every minute. So it's like you get a drip, then 1 minute there's just a little drop forming, one more drip, etc., etc., etc. Okay. Now if I gently increase the flow rate, and there are experiments on YouTube that you can see. I'm pointing you to one that I like with a channel called Veritasium. So if you increase the flow rate very gently, you'll go into a 2 drip state. First thing that will happen is that the time period between drips would decrease. So that's the first observation you will see. Then as you move forward, you will see a drop followed by a small drop. It would go drip, 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 drip. So there's a pattern still, but that pattern repeats in twos. Now, beyond that point, kitchen faucets don't give us the controllability, but people have done more controlled experiments where you can even ever so gently increase the flow rate, and you'll see patterns of 4 drops dripping right behind each other. Okay? And then going forward and forward and forward, you see this state where you simply cannot predict what the time period, what the inter-drip time spacing is going to be. The inter-drip time spacing becomes very unpredictable at some point when this dripping faucet goes into a chaotic rhythm. The key word in this paper, the title is very interesting. They call it chaotic rhythm of a dripping faucet. So there is still a certain pattern, but that pattern has all the signs of unpredictability, randomness. We will see examples of where this comes from. There's a very beautiful example we'll come to a little later. Yeah, as I discussed, weather prediction. The problem with weather prediction is that even if let's assume for a moment that all weather patterns were laminar, as ridiculous as that sounds. Ever so slightly, there was a point where a pattern had to make a decision whether to go left or right. That would constitute a separatrix, and that separatrix is sufficient for this. And if something like that were encountered time and time again, that weather pattern would become unpredictable beyond a certain spacing in time. Okay, that's you can read more in this paper by Slingo and Palmer, but essentially this uncertainty in weather and climate prediction comes from this core idea that there are unstable uh, separatrices. There are unstable patterns that are encountered in the process of this weather pattern evolving. I'm not going to dwell much on a lot of these models. You saw the double pendulum. The double pendulum is basically a two mass, two body problem, as they call it. And our solar system is at least a 10 body problem. If not, if you include all the moons, then you have a much more complicated system. And if a two pendulum system cannot be guaranteed to be in a stable motion, isn't it a miracle that our solar system is still showing some time periodic motion? Now, some may argue that we are only in that initial 3.2 second phase of the solar system, and that things will become unpredictable down the line. And there are examples in the literature that show that this is actually what they call stable chaos. I'll let you read more about this in the example in the reading material that I've indicated. Now, I'm not an expert on all this. Let me be very clear. These are all topics that I have cursorily read and understood just to kind of appreciate this world of chaos. So that's the reason I want to point you to the experts in the field. Anytime you have a periodic signaling, and that periodic signaling undergoes a process to kind of become more and more complicated, there is a possibility of chaos emerging. Same goes with arrhythmic heartbeats. So this is a very interesting problem. One of my colleagues is also interested in this. The core idea here is our heart beats in a very periodic pattern, and it's a highly nonlinear system. If you write down a set of equations governing the generation of this pulse. Now, this pulse separation has many different time frequencies, but if the under certain conditions, it shows what is called arrhythmia, which is lack of this rhythm. And this arrhythmia occurs in short spurts. And when these short spurts become longer and longer in duration, then you have a transition to a more or less chaotic system. Okay, so in order for us to make mathematical inroads into this world of chaos, you have to understand two concepts. Okay, what's called a pitchfork bifurcation and a limit cycle. So I'm going to briefly go over them. I'm going to take a very simple system that I've defined here. It's a 2 degree of freedom system. Mu is a parameter. Now, if you write down the set of for all values of mu, x equal to y equal to 0 is an equilibrium point, as you'll see. So for mu equal to minus 2.5, minus 2, you see this is the only initial condition, only attracting solution in the world, in the domain. So you can start with any initial condition, let's say there, this trajectory is going to evolve towards that state. If I start with an initial condition there, it's going to evolve towards that state. Okay. Now this is the attracting solution here. Now for mu equal to minus 1.5, which is beyond a critical point when two more equilibrium points evolve. So you see the 3 points marked in red. I'll call them stable 1, stable 2, and unstable 1. Now the solution at x equal to y equal to 0, you can show from linearized stability at this value of mu, you can show that this equilibrium point at x equal to y equal to 0 is unstable, whereas the other two solutions are attracting. So now there is a trajectory here, something that looks like this. If I start to the left of that trajectory, these trajectories evolve towards this condition. If I start to the right, these trajectories evolve towards the other state. Similarly on this side. Okay. So this is a simple example of what is called a pitchfork bifurcation. So what used to be a single stable solution, as this parameter is varied, becomes unstable. And in place of that one unstable solution, you have two stable solutions that branch out at a critical value of mu. Okay. Now, like I said early on, this kind of unstable separatrix. So this is our separatrix in this problem. You can see in this particular case, because it's only a 2 degree of freedom system, I can actually shade a region here and say all initial conditions on this side are attracted to S1 and the initial conditions on the other side are attracted to S2. Okay. The second point I want you to appreciate is what is called a limit cycle. Okay. So in the case of a single degree of freedom nonlinear system, you have equilibrium points that attract or repel. In the case of those are the only equilibrium solutions possible, or attracting solutions or repelling solutions possible in a 1 degree of freedom system. The moment you evolve into a 2 degree of freedom system, in this case, I've taken what's called a van der Pol oscillator. You can see that's the equation governing a van der Pol oscillator. For you'll see this value of mu change as this video evolves. For values of mu below a certain critical value, x dot equal to x equal to 0 is the only equilibrium point. Okay, it's an equilibrium point. Okay, so you can see that in this particular case, what this video is showing is that you start with an initial condition somewhere here. It's going to spiral. The solution or phase trajectory is going to spiral towards the only attracting solution in town, which is x dot equal to x equal to 0. Now, as I continue playing this video, there's a sharp critical value of mu at which you see these videos down here. At mu equal to 0 and any value of mu greater than 0 gives rise to a limit cycle. In other words, this little circular trajectory at mu equal to 0.1 and at mu equal to 1, you have another trajectory here. This trajectory becomes an attracting solution. So 1 second, for some reason my screen share has failed. We need to share screen again. I'm coming back, man. 1 second.
Mahesh is coming back. He has some internet issues. He's on the way, trying to reconnect.
Let me, my tablet seems to have dropped off. I'm going to come back in just a minute. Shine, I don't see the share option here. I think. Do you mind making?
The share option is still being shown on the tablet.
1 second. I'm trying again. Okay. For some reason I can't share it. Can you?
What I'll do is I'll just change it for temporarily.
Yeah, and bring it back here. Yeah.
Yeah. So, well, I don't see the second Mahesh. Okay, I got it.
Yes. Okay, good. Okay, sorry about that. Looks like we are back in business. So you can see that there are multiple examples where these limit cycles occur. So let me complete what I was saying on this slide here. So there is this at a critical value of mu, in this case mu equal to 0, the system develops, and in this the original equilibrium attracting solution becomes unstable, and now the only stable solution, the stable attracting solution in town, is not a point but an object like a limit cycle. It's a two-dimensional object in the two-dimensional space. Okay, and the size of that object, the size of this limit cycle, kind of increases. So you can see that this is only a small limit cycle, much bigger, and it kind of increases in size. There's a very nice pattern that describes how the size itself evolves. But any initial condition, say starting here, is now going to spiral out until it reaches that solution. If you start with an initial condition outside, that trajectory would evolve towards this limit cycle. Okay, so now what happens when the limit cycle becomes unstable? That's the question where chaos becomes interesting. For a limit cycle to become unstable, you need to go beyond 2 dimensions. Although there are limit cycles that are unstable in 2 dimensions, okay, I'll try to do this presentation from this mode because for some reason, sorry. So there are several examples of these limit cycles. You see in this particular case, the buffeting of a wing of an aircraft that you see here is a case of a limit cycle solution. Similarly, the video of a beating heart is actually a limit cycle. And for some reason, this video is not playing now, but it played just a moment ago. Briggs-Rauscher is an oscillating chemical reaction, and it shows some very interesting patterns for limit cycle again. Okay. So in order for us to understand this evolution between a stable equilibrium point to a limit cycle and then on and on and on, one of the most beautiful example problems, which actually is more than just an example, is what's called a logistic map. So let's understand what this logistic map is. It's a very simple map equation. That is, if you start with an xn, r is a parameter. If you start with an xn, you compute the next value of x in terms of as xn plus 1 as simply rxn times 1 minus xn. Okay, so if, and you can very clearly see that if xn equal to 0, then you have xn plus 1 equal to 0, which means it just, if you start with xn equal to 0, it's not going anywhere. Now n is the kind of the number of iterations of this logistic map. So if you start with something that is, if you start with an r equal to, let's say, 2, okay, you can start with an initial condition. In this case, the student started with an initial condition 0.1. It evolves and then it reaches a pretty stable state. It reaches a stable state at some point. So for every r value, at least for a certain range of r values initially, you'll see that this xn reaches a nice stable state. Let's continue on. You'll start to see that very close to 3, you start to see some oscillation, some overshoot, but then it continues to converge to a stable solution right there. Beyond 3, now this solution is not reaching a steady state, is not reaching a stable equilibrium attracting solution, but it is continuously oscillating between 2 solutions. Okay. Now, that is, if you plug in this value of the solution, so let's assume I have this kind of a oscillating pattern. If I plug in that 1, I get this 2. If I plug in 2, I go back to 1. So it simply oscillates between 1 and 2 and 1 and 2, etc. Okay. Now, if I continue where this video will take us, I'll stop there. This is at 3.7 of value of R. I'll try to pause it a little before that. This is 3.4, where you still see that it is oscillating between two states. This is 3.6, where if you notice carefully, there is a repeating pattern. You see 1, 2, 3, 4, 5, 6, 7, 8. So there is a repeating pattern you can see. But beyond a certain point, it goes into a fairly unpredictable kind of a final outcome at the end of 100 iterations. So there is no pattern to this. So what started out, so in order for us to understand why this evolves in this fashion, so let's look at this thing called the cobweb diagram. So what we've done here is, how does the solution converge? So for the cases where it does indeed converge, so there are two possibilities. So initially, you'll see that as long as what you see, the red curve is basically this function. So the red curve is the graph of R times xn times 1 minus xn. So I start with an initial condition, in this case 0.2, and then xn plus 1 would be whatever is the value of the function at that point. And this line that you see is basically xn plus 1 equal to xn. The graph of xn plus 1 equal to xn, which is basically a 45-degree line. So I go read off of that. Now that becomes my next value of xn. And I keep doing this. You can see how this solution is gently moving towards 0. So as long as this parabola is not tangential to the line, to the 45-degree line, the solution at x equal to 0 is attracting. If I go beyond that, let's say to that point, you'll see that now there is another solution. This point here has now become the attracting solution, and the solution at x equal to 0, which is still an equilibrium point, is an unstable solution. Now let's move on. So beyond a particular point, you start to see, so let's say this is at 3. So at 3.25, you can see how if I plug in a particular value if I start with this 0.2, I do the same cobweb kind of a thing. I'm forever going to jump between two solutions. The one near 0.8 and the one slightly less than 0.6, about 0.5. So I'm going to continuously jump between these two solutions. So if I plug in the value at 0.8, I get the value at 0.5 and vice versa. Okay. So now if I continue this evolution, you start to see that where you used to have one square, you now have two squares that have evolved, which is what is called a period 4 solution. That is, it is going to oscillate between 4 values. Okay, now, and then on and on and on, as you get closer to 4, the entire phase space, the entire space of outcomes between 0 to 1 are all possible for any given initial condition. Okay, so now why does this is a very simple equation. Why does it do this? So let's go to our notepad and just quickly understand. Remember the core idea, I need unstable separatrices. Okay, so where do I see that? So let's go, actually, let's continue this here. So I'll come to this Feigenbaum constant discussion a little bit later. But this is a good point. So if I start with an initial condition, so any initial condition, until I reach a value of R of about 1, the only attracting solution is xn equal to 0. So I can start with an initial condition there, and like I showed before, it's going to evolve towards this solution. Beyond 1, you start to see this other branch appear. Okay, so if I start with an initial condition here, it's going to evolve this way. If I start with an initial condition there, it's going to evolve this way and be attracted towards that branch. We saw the cobweb evolution. Now at this critical value of R at 3, you start to see this bifurcation, that if I now start with an initial condition here for a value of R greater than 3, it's going to evolve to this point and then keep jumping between these two states. So I'll call this 1 and 2. But remember, this branch was a stable branch until R equal to 3. And a stable branch is basically where it's a solution to this equation at R equal to 3. Until R equal to 3. So it continues to, I'll write this slightly more formally with a as f of xn semicolon R equal to 0 to indicate R is a parameter. Now beyond R equal to 3, this solution branch does not disappear. It cannot disappear, right? Because by parameter continuity, if I have a solution that was present for R less than 3, slightly less than 3, it simply cannot disappear for R greater than 3. So in this case, at least, you can show that it does not disappear. You can have a case where it becomes complex from being a real solution to a complex solution. But in this case, there is actually a real solution. And that real solution branch will continue for R greater than 3 also, except it is unstable. So you can now imagine that I have one more solution that has evolved, which is jumping between a state 1 and a state 2. But in the middle, you have this unstable separatrix. Okay. Now, beyond a second critical value of R, you see again this unstable branch continuing. Okay. But you now have a period 4 solution. Now imagine this happening over and over again. So a stable branch bifurcating into a period 2 solution, then a period 4 solution, leaving behind these unstable separatrices. Okay, so every time a solution encounters the unstable separatrix, it has to make a decision whether to go left or right, just like the coin. And this decision to go left or right brings in the sensitivity to the initial condition. And beyond a certain, when you have, so now to the Feigenbaum constant idea. As it turns out, the critical values of R at which these bifurcations from period 1 to period 2 to 4 to 8, etc. happen, have a rhyme and a rhythm to them. And that when you take this ratio of Rn minus Rn minus 1 divided by Rn plus 1 minus Rn, that is the period 4, I'll call this R4 minus R2 divided by R2 minus R1, meaning to go from a period 4 solution to period 4 to period 2, the difference between the R values at which these bifurcations happen, divided by the period 2 to where the period 1 bifurcation happened, etc., for n becoming large. This evolves to a constant. This is a universal constant known as the Feigenbaum. This is known as the Feigenbaum constant. And some argue that this is as universal a constant as pi or e or any of these other numbers that we are used to seeing as having a physical significance and being irrational. Now, so you can imagine this cascade of these periodic bifurcations resulting in something that is that's got a lot of unstable separatrices embedded. So remember, this unstable separatrix does not end, at when you undergo a periodic bifurcation to period 4. It continues on. So imagine at period 16, you have 16, you have 8 plus 4 plus 2 plus 1. That many unstable separatrices continuing into the phase space. Okay, so this now makes the phase space beyond a certain point, so densely populated with these separatrices that it gives rise to these chaotic systems that become very sensitive to initial conditions. So here is a zoomed in view of that same diagram in the region where you start to see the period 2. This is a period 2 bifurcation. This is a period 4, sorry. This is a period 2. Then you have a period 8. Then you start to see a little bit of the period 16. And numerically, it becomes very difficult to capture period 32, etc., etc. But they all accumulate because of the Feigenbaum constant. They accumulate into a number somewhere here, beyond which you can expect chaos. Okay. So that brings us to a very simple a discussion of what are the different ways by which I know when the system is becoming chaotic. And I'm not going to dwell deep into these 4 routes that are now kind of well discussed in the literature. One is called the period doubling route, which we just saw in the case of a logistic map. Then there is the intermittency route, which is basically where you get bursts of periodic solution or bursts of chaotic solution embedded in an otherwise periodic state, and then and when the time span of these bursts increase, it gives rise to full-blown chaos. Then there is the RTN route to chaos and the crisis routes. I'll mention it, and those of you that are interested should read more about that. Now, how do I know when a system is chaotic? Like I said, at the core of a chaotic system is this sensitivity to initial conditions. So the test is also based exactly on that idea. I'll start with 2 initial conditions that are very, very close to each other, delta naught away from each other, and let the system evolve n iterations in the case of a map or in time. I let it evolve forward in time, so to say, and see this and measure the separation delta n after n iterations, and then compute this parameter lambda, which is 1 by n log of delta n by delta naught. Now, why am I doing it in this fashion? Because delta n, if you look at this, goes as delta naught times e power lambda n. So the core idea that Lyapunov found was that these trajectories not just diverge, but they diverge exponentially fast in time. Okay. So the parameter lambda will now tell me how fast is the trajectory going to diverge. I'm really not interested in the value of lambda. I'm only interested in the sign of lambda. So lambda greater than 0 tells me the system is chaotic, and lambda less than 0, all I know is it is not chaotic. I don't know anything else about it from the Lyapunov exponent computation. Okay. So let's see what the Lyapunov exponent looks like for the logistic map. So we compute the logistic map, the Lyapunov exponent for the logistic map. You can see that for all states less than a certain value right there, lambda turns out to be negative or very close to 0. And there is a critical value beyond which lambda becomes large and positive. Okay. So this separates the region where one would expect chaos. So in other words, at beyond a value of 3.6, let us say, wherever I start on the initial condition space, they are going to diverge at some long enough time and exponentially fast. And however small delta naught is, these trajectories will diverge exponentially. So just to show you that this works, if I took different initial conditions, lambda doesn't, it makes no difference. I can start with whatever initial condition. Where lambda becomes positive, lambda does show a positive and increased, shows a positive value of lambda. And where it does not, you can see this being negative. So there is like I said, this whole field of chaos owes itself to Lorentz, who started working on weather modeling. And it's a very simple set of equations, actually. The only two nonlinearities are those product terms that you see in those two equations. This is a 3 degree of freedom system. And what I'm showing here is an animation of this Lorentz system. Evolving from each dot in this animation is one initial condition. Okay, so you can start with a set of initial conditions. Okay, so you can start with a set of initial conditions. Therefore, three different values of, you see this Lorentz system evolving for three different values of sigma, beta, and rho. For the leftmost panel, you can see that all the initial conditions essentially kind of converge towards two stable equilibria. For the intermediate state, it actually, if you let the system evolve long enough, these solutions go into a nice limit cycle. It's a limit cycle or any cycle is a one-dimensional object embedded in this case, in three-dimensional space. So all the points evolve towards a kind of an 8-like limit cycle, whereas the rightmost values that you have for sigma, beta, and rho is where you have a fully chaotic system. In this particular video, it's not very clear, but all the points they're not just scattered all over the three-dimensional box. Even though I may start with initial conditions that are all over the three-dimensional box, they are attracted towards a lower dimensional object. And that is what we were talking about as the correlation dimension when we discussed randomness versus chaos. The correlation dimension is a thinner object. Thinner in the sense that it is not exactly a two-dimensional object, but it is a thinner object embedded in this three-dimensional space. And all solutions everywhere in the 3D space are attracted to that thinner object, but unpredictably. You don't know where which initial condition will end up. That's what makes the Lorentz system kind of a very interesting system. But actually, the Lorentz system has been studied quite widely, and so is the other system I'm going to talk about, called the Rosler system. This is actually simpler. Okay, it's got only one nonlinear term right there in this product. So these are three videos showing the Lorentz system, showing the Rosler system. They are starting with an initial conditions that you can start with initial conditions filling the entire 3D box. Doesn't matter. Okay, but we are seeing this video of those initial conditions evolving in time. The first video is for A equal to 0.4, B equal to 0.3, and C equal to 1.4. You'll see that in due course of time, all the initial states are all embedded into a nice limit cycle solution. That is, they're all going to essentially are attracted towards this limit cycle solution. The middle panel is also a limit cycle solution. As you will see, it is slightly more complicated in topology. It is kind of circling on itself, but never crossing, remember. Okay, so this trajectory is still a limit cycle. It just is executing multiple periodic oscillations. So if you think of it, if I was to now convert this Rosler system into a map, imagine I draw a plane right at z equal to 1. Z is my vertical axis. If I draw a plane at z equal to 1 and look at where this trajectory crosses in the upward direction. Okay. In the first case, there's only one point where the trajectory crosses in the upward direction. In the middle panel, there are 2 points where the trajectory crosses the upward direction. Actually, if I was to draw it slightly below that, there are actually 3 points. In this case, this is a period 8 map, meaning it is going to go from 1 to 2 to 3 and then oscillate back and forth. That's because the limit cycle is circling upon itself kind of 3 times. Okay. In between these two, there is another state where it only circles upon itself twice. At the rightmost panel is the part where it is in full-blown chaos, where you see that all these initial states are embedded in an attractor that's got a topology of dimension less than this box, less than 3. So it's like an object like that, except it is not a perfectly thin sheet that would be dimension 2, but it's got a thickness to it. So this dimension, the dimension of the object, is what we earlier called the correlation dimension. So the unpredictability arises in this case from what is called a homoclinic orbit. You'll see this, the trajectory that is shooting up and coming down towards the origin essentially is causing this, where is kind of the origin of that instability. So again, the idea that you have multiple unstable separatrices embedded is still true. That is, for c equal to 1.4, there is a simple limit cycle. C equal to 2.63, there's a next level limit cycle. C equal to 4.4.9. At c equal to 2.63, the first limit cycle is still a possible solution, except it is unstable, and therefore it repels and becomes a separatrix. And these, as you go through a series of bifurcations of these limit cycles, from a period 1 limit cycle to a period 2 to period 4, period 8, because it circles upon itself more and more, you can see that not only is the topology of the limit cycle become more and more complex, but you have an infinite number of these unstable limit cycles that are embedded once you reach a system at the full-blown chaos state. And any initial state has to kind of navigate this minefield of unstable separatrices to wind its trajectory. Now you can see every time there is a certain inherent unpredictability that will arise out of forcing a trajectory to go either left or right. Remember our original point. So that's kind of the story of chaos. So let's kind of wrap up with some simple concluding notes. And we'll spend the next 15 minutes with questions. So those of you that have questions, start typing them in the chat box, please, and we will try to look at them in some order, and I'll let Anubhav handle the questions. The first point I want you to remember is sensitivity to initial conditions. This is a requirement and is sufficient. Second, the whole a chaotic system is at the very heart of it a dynamical system, obeying Newton's laws, or obeying some, not Newton's laws, but a dynamical system that is got no stochasticity to it. Okay. And the last point to remember is that you need these unstable separatrices. I'll use lay words here. Please excuse me. I'll call them trajectory meandering, because at the end of the day, these trajectories, the trajectory itself is a one-dimensional object always. It cannot intersect. It is in a space that is, some three-dimensional space. So a 1D kind of a trajectory has to snake through all these minefield of these unstable separatrices in order to make its way in a dynamical sense. Okay, and this trajectory meandering leads to chaos. Good, I'll stop here. There's another 15 minutes or so for questions. Anubhav, I'll let you help me handle this question part.
Thank you, Mahesh, for a detailed introduction and I hope the audience also quite learn something a lot of new. So please go ahead and raise your hand if you wish to speak. We'll unmute you. Meanwhile, there are already few questions in the chat box, so I'll take those. Uh, so there is a question from Rajesh Kumar. So is limit cycle a 2D analog of an attractor point like attractor curve?
So an attractor curve, if I understand you right, in a 1D sense, you only have equilibrium points. In a one-dimensional nonlinear system, you only have equilibrium points, stable or unstable. Now, those equilibrium points are functions of a parameter that you have in the system. It could be more than one parameter, but that is, I'm presuming, what you call the attractor curve in a one-dimensional space. In two-dimensional space, you still have equilibrium points, as you saw even in the case of the Lorentz system, but you also have this additional possibility of a one-dimensional object, not just a zero-dimensional object, but a one-dimensional object becoming either an attractor or a repelling solution. So it's an added feature in two-dimensional nonlinear systems. Now, when you get to a minimum of 3 dimensions, you have this added feature of an attractor, which is not a limit cycle, not an equilibrium point, but a finite dimensional object that attracts all solution towards it. You saw that in the case of the Rosler system or the Lorentz system. This is only possible when you have at least a 3 degree of freedom or in a 3-dimensional problem. Does that kind of answer the question? So as the degrees of freedom increase, you are getting kind of more and more complex objects that are either attracting or repelling.
There's another question in the chat box. Is limit cycle present in every chaotic system?
So I'm going to assume that you are talking about systems that are time continuous, not maps. Like we said, there are multiple routes to chaos. Certainly in the case of the period doubling route, my understanding is, yes, you should have limit cycles. If you have a period doubling route in a time continuous system, you will have embedded limit cycles that are all unstable. Okay, now in the case of the intermittency route to chaos, I'm not so sure. So I kind of in detail discussed the one that is more intuitively easy to explain in a short lecture, but I'm not so sure if all the routes to chaos require an embedded limit cycle. But I think the core idea will still remain. Even in the case of a homoclinic bifurcation leading to chaos, you still have this core idea of a separatrix and multiple separatrices. Somehow my intuition is still centered around that. So I'll leave it at that.
Next, maybe we could take Danish. He has raised his hand.
Yes.
Please go ahead and ask the question. You are unmuted.
Okay, so thank you. So in one of the graph, you mentioned a number, there's a Feigenbaum number. So beyond a Feigenbaum number, the system goes into chaotic state.
No. It's not beyond the Feigenbaum number. Remember the value of R at which, let me go back to that slide. It makes it easy for us to talk about. So there is a value of R at which your zero solution becomes unstable, right? The zero solution it still persists except it is unstable. Then you get this solution branch, and at R equal to 3, the equilibrium solution is replaced by a 2-period solution. And at another value of R, your 2-period is replaced by a 4-period solution. And another subsequent value of R, that 4-period is replaced by an 8-period solution, and on and on and on and on. The difference between the value of R at which 8-period solution starts and where the 4-period solution starts, divided by the difference where the 4-period solution starts and the 2-period starts. That ratio, as n tends to infinity, becomes equal to the critical value. That's kind of the whole argument. Does that answer the question?
Yes, sir.
So it is the value that you saw there, 4.449, etc. is not actually a value of R. It is not actually it is not the value of R, it is the ratio of the differences in R that will cause all of these values of R to come at us quicker and quicker and quicker, and therefore there's an accumulating point at which you start to observe full chaos. That's
So
somewhere
yes,
near 0.6. Okay,
so
next question.
So I think we'll take some from the chat box. There's one. Does it mean that emergence of branch of stable, unstable fixed points from the term periodic doubling, fourth doubling?
Does it mean that emergence of branch of stable? So for example, in this case, you have one solution here that is unstable. You have one solution branch which is somewhere in the middle here that is unstable. And so there are multiple unstable trajectories that continue into this space where you see chaos, right? And potentially, because you have an accumulation of these bifurcation points from period 4 to 8 to 16 to 32 to 64, etc., you have a lot of unstable trajectories that are remnant. And so in the presence of all these unstable trajectories, and in the absence of an equilibrium solution, the phase trajectory is left meandering in that space. The phase trajectory kind of essentially, that's kind of where the signature chaotic behavior is manifest. I hope I answered the question. The question is not very clear to me, Devanand.
We have another question after that. In the computational studies concerning studying stability, how is the error propagation due to finite precision of calculation accounted for?
So that's a very, very difficult, very interesting question, actually. So you're asking, if the inherent mathematical model is chaotic, how do you compute stability, or how do you study stability? So the only way that I know is to first compute your Lyapunov exponent. So if you compute the Lyapunov exponent and it is positive, then it is very difficult to calculate error propagation. At least for sure the error propagation would be exponential after that. Below that, of course, you can kind of estimate what the error propagation is. So in fact, there is a whole school of literature that argues that turbulence is nothing but a period doubling route to chaos. People have done analysis of experimental data to show that, at least they show that it's just a sequence of period double states that results in this chaotic state called turbulence, and that there is nothing inherently random about it. So fundamentally, if you're doing computational studies of a chaotic system like Lorenz was doing, you really cannot compute error due to finite precision if or you can only, what you do know is the Lyapunov exponent. You can compute the Lyapunov exponent. And once you know the Lyapunov exponent, that in a sense tells you the rate of propagation, because e power lambda t is the kind of the rate of propagation in time. I hope that answered your question, Rajesh.
I'll take the next one.
Yeah.
So when we say sensitivity to initial condition is the route to chaos, in case of nonlinear system, the sensitivity to initial condition shall be a function of the initial conditions itself. In that case, does the occurrence of chaos depends on the deviation of initial conditions in any direction?
Not really. So I showed you the example where even for the logistic map, you can show two different initial conditions giving you the same Lyapunov exponent. So certainly the Lyapunov exponent that you compute from various set of initial conditions would not be very different. And more so, if I'm only interested in the sign of the Lyapunov exponent, that certainly will not depend on the set of initial conditions. Now, in a typical, when you've chosen a set of parameters in the problem where your system exhibits full-blown chaos, then it is exhibiting chaos for all initial conditions, not just for a limited set of initial conditions. So the lambda computed would be applicable to all states.
Then there is a comment, isn't the mathematical formalism built upon the inference from data obtained by doing calculations?
So that's where I think, so the whole premise of chaos theory is that what looks absolutely, benign and governed by a very well-behaved continuous, so the variables are all continuous, right? They're all, they exhibit, C infinity, C0, C1, they exhibit the solution trajectories are always going to be differentiable with respect to time infinitely to infinite, degrees of differentiation. So you are looking at a time continuous system that shows no signs of repeating and is embedded in a finite dimension, in a finite dimension attractor, which is more than 2 in most cases, right? So this is so in order to really understand whether it is inference from data or uh, inference from data, so you are really only showing the idea that I can start with any pair of initial conditions and the solutions will diverge exponentially. And so every initial condition leads to a unique trajectory that will not cross paths with any other trajectory, right? And those are the only guarantees that we have from both the minimal dynamic, from basic dynamics and from the chaos theory. So really, I don't know if one would argue that the mathematical formalism beyond this is really built only on inference from data. I think at this point, those are the kind of the telltale signs of a chaotic system, as I understand it.
There is a question from Hari Prasad. You had mentioned that in the phase portrait during chaos, every state is achievable. Can we say that if we wait long enough, a chaotic system will eventually cover every point?
So again, in principle, I think yes. But then how would you show it? I don't know. Look, I'm not a mathematician. I have not looked at the formal proof of whether it will actually completely occupy the space. Now, the problem is this, that let's say if you take this, I like the Rosler attractor a lot because it's a very beautiful system. So if I play this video, so I'm starting with an initial condition set that is like very closely embedded, but then they will evolve into a kind of a figure that looks like that. It's got a finite thickness. The trajectory itself is a one-dimensional trajectory, right? So if you say a one-dimensional trajectory will never cross itself and will avoid all the unstable equilibria. So except the unstable equilibria and the points that unstable limit cycles and the points on the unstable limit cycles, which are infinitely many, I would expect it should sample the entire attractor. Okay, other than that, I don't know what else to say. I'm not a mathematician beyond that point. Okay.
Any other question? Either you want to ask in the chat box or directly speak. Okay, if there aren't any other question, thank you, Mahesh, once again for this wonderful talk.
Thank you.
And Sayan, do we meet back again at 5 for the next talk?
Yes, so at 5 o'clock we have Professor Arijit Samal from IMSC who will be giving a talk.
So this talk was to go till 4:30, right? I hope I didn't.
Yes, you are perfectly on time.
Okay, great. Thank you.